Hi, this is a follow-up video to the Rigol DS1054Z firmware issues that were found in a previous video. If you haven't seen it, click here or link down below and watch that first, because otherwise it may not make too much sense. Anyway, Rigol have finally released some new firmware that they claim fixes not only the 5 microsecond jitter issue, which we can see here, but also the AC trigger coupling jitter as well. So I haven't installed the new firmware yet, so we'll try it. Now, they have actually released a beta trial firmware fix for it before. They put it on the EEVblog forum, so huge thumbs up to Rigol for actually engaging directly on the EEVblog forum and actually releasing it there so people could trial it. But unfortunately, that one didn't work, and I didn't get around to trying it myself, but a lot of people on the forum tried it, and they said, nah, didn't fix it and had other issues. It was locking up the keyboard and doing all sorts of weird and wonderful stuff. So Rigol pulled that before I got a chance to try it, but they're finally in the new year now, so happy new year to everyone, by the way. And Rigol have released the new firmware, so let's give it a whirl. But before we do that, a few users on the EEVblog forum actually went to a lot of trouble to try and figure out exactly what was causing this 5 microsecond jitter issue, and they pretty much came to the conclusion, and I think they're right, that it was something to do with the PLL, the phase lock loop inside the 1054Z that generates the main sample and FPGA clock. Now, this is a lower frequency crystal, and there's nothing wrong with the crystal itself, but it's the PLL chip itself and the loop components around that. And this is a programmable chip, and they discovered that it looks like it's not locking properly, and it's getting jitter and doing all sorts of weird things. So that would explain it. If your main clock for your ADC and sampling system and, you know, everything else, your main FPGA is jittering badly due to a poor PLL lock or something, or, you know, some sort of issue to do with the PLL, then, well, that's going to upset the whole apple cart. And we're pretty sure, I think most people are pretty sure that's actually what's at fault here. And Rigol they haven't admitted that, but they have said that they have updated the coefficients which get programmed into the PLL chip when the unit boots up. And, well, that's, you know, most likely to be the issue, or it could be that plus a combination of some stuff in the sampling FPGA as well. We don't know unless Rigol actually come clean and admit exactly what the issue is and what they did to fix it. But I thought we'd not only reproduce the problem here before we update the firmware, see if it works, but crack this thing open, have a quick sniff around with an EMC probe, see if we can get that signal. Let's give it a try. So consider this our before shot for the 5 microsecond jitter. Here it is. We've got a 20 megahertz square wave going in. We've got our 5 microsecond precisely offset, and I've got infinite persistence on there. And you can see pretty much it's doing just maybe a division, maybe, you know, 1.5 little graticule positions there. So it's 5 nanoseconds per division. You know, it looks like it's maybe 1.5, almost 2 nanoseconds jitter on there. Not a huge amount, but as I said in the previous video, my unit is not a particularly bad one. Some people have it really horrifically. So, and if I push the horizontal to go back to no offset at all, bingo, you'll see it vanish. Alright, so I cracked this open, and what we're going to use here to measure the PLL clock in this thing, I'll show you a close-up in a minute. We're going to use this you've seen in a previous mailbag. This is the TechBox EMC probe set, and we've got the 3 H-field probes here, the magnetic field probes, and the one we're going to use is the E-field probe here. The magnetic field probes will work, especially the smaller loop one here, but in this particular case we really want to get down, isolate components right there. So the E-field probe is better with its tiny tip, and really we're not talking about large magnetic you know, loop currents and things like that. So the E-field probe is a better choice for this. And we've got our wideband amp here, so that goes from 3 meg up to 3 gig, so that should be pretty good. We've got our Rigol DSA815 spectrum analyzer here, and we can now sniff around. What I'm going to do though is I think I'm going to have to set up a second camera so that I can show you probing around here at the same time as the result we get on the screen here. Now, here's the main culprit right here, the Analog Devices ADF 4360-7 here. And this is an integrated synthesizer and voltage controlled oscillator. It's basically a PLL which multiplies the main crystal here, 25 megahertz. You can see that oscillator. Now, this oscillator is going to have bugger all jitter. That's not going to be the issue. It's going to be this phase lock loop. And you can see, so it multiplies that frequency based on these loop filter components around here and the internal coefficients that have been programmed into it by the firmware at startup. And then you can see it's a differential output here, and that is the main clock which goes into your ADC over here. I'm not sure if it actually goes anywhere else, whether it's goes into the FPGA or such, but it looks like it might just be for the ADC here. So let's give it a burl, see if we can sniff around here and get the signal out of this thing. Now, this is certainly not a tutorial, so I won't bother explaining how PLLs work and how the loop filter components and coefficients and all that sort of jazz works. But these components here, they will be our loop filter components. These are, looks like we've just got some output AC coupling here, and that's about it. So what we can do is use our probe to sniff around here and see if we can get that output clock signal. Alright, let's have a probe around with our E-field probe here, and you can see how I said it's got a tiny little tip on there, so it really allows us to get in here and look at our components. Now, I've set up the DSA815 spectrum analyzer. Well, I haven't set it up, it's just like power on defaults, it's just full span like this, so we just want to have a look to see if we can find the signal. Now, if we get our probe in here like this, and we go very close to the output pin here, it's a single-ended output on our clock, our 25 megahertz clock. There we go. You can see the clock and all its harmonics right down there. No problems whatsoever. So if we can now go over our PLL chip, we can't see anything on the PLL chip. You can see how discriminatory this probe is. We've hardly moved it and it's vanished. Now let's move the probe over these loop components up here. Bingo! Look at that. There is our PLL output frequency right there. Massive spike. And look, I moved that away just a little bit from those components or back over the chip, and it vanishes. So this is how useful these damn probes can be. You can get right in there, and of course we can go to the output traces here, not nearly as the differential output here, not nearly as high amplitude as what we get with those loop components. So really, anyway, we're getting quite a decent signal on there. So now we can center our spectrum analyzer here and just have a look for any side components on there. See how clean that is. But as I said before, we can use this tiny H-field probe here. So this is the smallest one out of the three I've got. So it's got the smallest loop area. So you'll get the best discrimination there. So let's put it over here. And look, we can put it over the ADC here, for example. And you can see like various components on the ADC there, which we couldn't actually see with the E-field probe. So this is going to pick up more, but it depends on the loop area and the current flowing. So here we go. Hey, there we go. There's our spike. That's actually, I think, bigger. Oh yeah, look at that. It's really gone to town there. Check that out. We're really picking that up, but we're also picking up, so we're picking up much higher amplitude than we were getting before, but we're also picking up lots of other crap down here as well. So for the purposes of measurement, I think the E-field probe is probably going to be the better choice here. We can really get localized in, but yeah, as far as amplitude goes, we are actually getting a higher amplitude there with that tiny H-field probe. But yeah, look, you can pick up a lot of crap at the same time if you're not careful. Whoa, look at that. And if we turn our marker on there, look, we can see that is bang on 1 gig because, hey, this is a 1 gig sample per second scope, is it not? That's exactly what you'd expect, and it is bang on according to the Rigol. Now I've got my probe over the loop components there. I've got some auto scale happening. We've got 1 gig center and it looks pretty clean like that with a span of 10 megahertz. But our bandwidth, here we go, our resolution bandwidth is the default 300 kilohertz here. So we need to really knock that down before we can start seeing some components in there. So let's have a burl at that and see what we get. And here we go. If we get a 4 megahertz span on here with a resolution bandwidth of 300 hertz, takes a while to build up there, but look at that. That doesn't look too crash hot, does it? And here it is, that'll do. Now, I don't really care about the particular details of what's actually going on here. All we want to do really, for the purposes of this video, is to see if this stays the same after our firmware change with the same settings, same probe position, everything else. I think we're going to see a fairly dramatic change. Now here's the interesting bit. I've changed the span here to 1 megahertz total, and look, we can see these peaks here. Here's our fundamental here, okay? And look at the deviation from here to here. The delta, I've set up a delta of those two markers, 100 kilohertz. Why is that significant? Well, our issue is a 5 microsecond multiple jitter problem. That means at every 10 microseconds it goes away. Multiples of 10 microseconds it goes away and comes back, etc., etc. Well, what is 10 microseconds? Invert that. It's bang on 100 kilohertz. Aha! Please excuse the crudity of the model. Didn't have time to build it to scale or to paint it. Now, I'll try and explain kind of what's going on here. Now, with our little Dave Cat drawing. Now, if we've got our trigger point here, okay? This is our, I know it doesn't kind of make sense the way I've drawn it, but stick with me. Anyway, if you've got the trigger point here, you've got your 1 gigahertz sample clock, okay? Now, because that is the trigger point of the oscilloscope, you're not actually going to see any jitter there because the clock can be jittering like crazy. You're not going to see it because at this point on the screen and on your waveform, because it's the same sample point each time. You're only going to see it when you shift the waveform in this direction and then view this one in the center 5 microseconds later. Okay, this is the problem. And let's say you view it 10 microseconds later. Well, there's our 100 kilohertz. Okay, if this main sample clock is jittering, effectively being modulated by 100 kilohertz, that's a period of 10 microseconds. So once again, you're not going to see it there because it's going to match up precisely with the jitter time. But if you go halfway, i.e. half that value of 10 microseconds, 5 microseconds, bingo, you're going to see all your jitter in there. And then likewise at 15 and so on. So I hope that's as clear as mud. I think I could have come up with a better explanation than that. Anyway. Right, so we've got that little baseline there. Now let's upgrade our firmware. For the record, this is what I'm running now, 4.01.SP2 on 1.1 board revision. Okay, let's update the firmware here. I've installed the file on the stick. That's all you're supposed to do. The .gel, there we go, bang, caution, newer software version detected. We're installing 4.02.04.07. Do you wish to continue? Please do not remove. Come on, you can do it. Could take a while. Should I twiddle my thumbs? I think it's worthy, isn't it? Come on. Come on. Anyway, what we really want to see is a change in that PLL, the PLL coefficients. Rigol have said they have changed them, so they have admitted that. So we should expect to possibly see a change in that spectrum there. Congratulations, update was successful. Now you can restart the oscilloscope and enjoy it. I will enjoy it, if it bloody well works. So, yeah, I guess we just depower and power back up. Remove the stick, of course. And as usual, this scope does take a little while to boot. which is a downside of modern scopes, but all with their new modern whiz-bang operating systems, you know, what do you expect? Anyway, we're in like Flynn. So the utility system information, so no problems at all. 4.02.sp4. I have no idea if this keeps the any upgrades and things you've got, or any software upgrades or anything. Presumably it would. All right, here's our test. I'm putting the probe basically where I had it before, and let's go in there and okay, here's the test. I'm putting the probe pretty much where I had it before, so let's do single shot and see what we get. Bingo! Significantly different. 1 megahertz span there. I haven't changed anything else on here. So the waveform you saw before was, this is what it has changed to. There you go. So they certainly have updated the coefficients of this down in here. They've changed that because it's got a SPI bus on there which interfaces to the main micro, and then it has to program in those coefficients based on the particular loop filter components they got on there. And there's a lot of tricky theory which all goes behind this, and well, yeah, I won't go into it, but hopefully Rigol have done their homework. Now let's repower it and see if there's any jitter. Alright, there's our 20 megahertz signal at no delay, 0.00000 picoseconds. Gotta be shitting me. Anyway, that's just crazy. So we'll change our horizontal here. Oops, sorry, we'll go this direction. So we'll tweak that up. I'm holding my tongue at the right angle just in case. And 5 microseconds. And ta-da! Look at that! That looks pretty good. You can't complain about that. Like, I can't zoom in any faster than that because that's the lowest time base is 5 nanoseconds per division on this 1054Z. You might get an extra step there if you've got the 100 megahertz model, but I've only got the 50 megahertz model. So there you go. That is gone, and I've got infinite persistence on there, of course. And let's just I'll hit the horizontal button, so we'll jump back. So like we can turn off the infinite persistence there. There we go. But it's certainly changed. So I can certainly consider that fixed, although I would have to go in and check for any other multiples in there or anything like that. But you can pretty much be sure if you can measure it on the spectrum analyzer, then, well, you should be able to actually calculate where any of these issues should be. But looks like they've fixed it, but that's fixed it for my scope. They had the same issue before when they released the beta version of this fix. It fixed some people's machines and everyone said, yay, problem fixed, thank you very much, Rigol. And then other people came out and said, no, made it worse. All sorts of things, because those loop components, they're going to have very significant tolerance, like 5-10% tolerance on those things, let alone over temperature and everything else that can be involved. So, you know, really, yeah, it's okay. It's fixed mine. So fantastic. I'm a happy little camper. Let's see if it's fixed the AC trigger jitter. So put that back to the start there. Let's go into our trigger jitter menu. You've got to go down here to setting, coupling, and this is trigger coupling. As I've done a video on, it is not input AC coupling. It's AC trigger coupling. Big difference. So let's do that, and ta-da! We're a happy little camper there. Let's turn off our infinite persistence because I was just varying the offset level control there. So let's go into display, change that back to minimum. Thank you very much. So I can change our level there, and of course it's going to lose it because I'm adjusting the trigger level, so it's obviously like gone above the waveform and it just doesn't know what to do. There we go, I've set it properly, the ×1 scale factor on channel 1 here. So yeah, you'd expect it to go off trigger at when it gets to about 2.5, because we're talking 1 volt, 2 volts, you know, 2.5 there, and that's what we start to see, and bang at about, yeah, 2.7 or something. So that's right, down on the negative side. So our AC trigger coupling is now coming back down. Whoop, let's go, sorry, let's go negative. And about the same, 2.6, oh, about 2.5 volts or thereabouts. Yep, so that's not too shabby at all. On first glance here, AC trigger coupling problem also fixed. Very nice. And if you're curious to know about the new PLL signal here, well, our delta there is about 68.334 kilohertz. So we need to invert and then halve that, and that gives us an offset around about 7.31 microseconds. And here we go, 7.31 microseconds. Well, I don't see any noticeable jitter in there at all. So, yeah, I think that's pretty well fixed. So although the problem's fixed, I did actually, if you probably watch this in HD, you can actually see a little bit of fuzziness to the line. There is a slight bit of jitter there compared to the regular one, but oh, you really pixel peep in there. But anyway, I still have a problem with this. Although, hey, the jitter problem on my particular unit is fixed, okay, fine, but this is a pretty awful clock. I mean, like I've zoomed in this a little bit. I've now got a 500 kilohertz span here, and I've got our delta. There's the delta on there. There's 67.5 kilohertz there, and then we've got another little peak which is showing itself here, and really none of this should be there, and it's like only like 37 dB down from the carrier here. I mean, it's pretty piss poor. So the output from that PLL is still not great. So I think Rigol need to fix that. I mean, they need to fix that solid, whether or not they can even tweak the coefficients even further, perhaps, and get it better, or whether or not they have to actually change their loop component values in hardware. And it wouldn't surprise me if Rigol just didn't mention this, and like all existing unit, and this firmware fixes all existing units, but secretly in the background, newer units might actually have different loop value components. That wouldn't surprise me at all, because this is pretty bloody awful. I mean, a proper one should be, like, it should look, none of this stuff should be here. It should be like right down here like this. It should be very nice like that. So we shouldn't have these components in here, but it doesn't seem to. I mean, I've checked the multiple frequency of that, and it seems to be okay, but yeah, that's still a pretty bad clock. But hey, I mean, Rigol are between a rock and a hard place here. They don't want to have to recall every unit that's already been sold to actually fix any hardware loop component values. That'd be absolutely horrendous, and they have to weigh it up against the actual performance of the scope. And well, if it's proven, hasn't been proven yet, but if it's proven that it fixes everyone's unit out there and there's no reports of it, different spreads of units, we've already seen that issue. A lot of people have a huge spread of issues. So if we can get all those same people and even more to report whether or not this is an issue, we'll know if it's a solid fix. And if it's a solid fix, well, it's a solid fix, even if this clock is still pretty crusty. Well, I think Rigol do need to fix this, though. I don't like it still. Gives me the heebie-jeebies. So there you have it. I'm pretty happy with the fix on mine. It seems to work well, but yeah, the proof is going to be everyone else when we've got actually, statistically significant numbers and spreads of units and component spreads and all that sort of stuff. So if it works out to be a solid fix, great. I'm happy, but yeah, there's still a chance that it may not fix everyone's unit. So that's going to be Rigol's problem. Oops, we've re-triggered there. It shouldn't have done that. Wonder why I did that. So yes, Rigol still need to be vigilant on this issue, and as I said, I still think they need to fix that clock, so that's pretty piss poor. But it's one of those arguments like, is it good enough to do the job? If there's no measurable difference on the scope, well, does that clock matter? Is it good enough? Yeah, ultimately, it's a bit academic that, okay, it's not the world's greatest clock, that's for sure. It's pretty piss poor, but if it does the job, on this particular hardware and nobody can measure the difference on the scope itself, then yeah, what does it matter? So I hope it's a solid fix. If it is, fantastic. But yeah, wouldn't be surprised if they sneak in a little hardware fix, and they, you know, like, this thing shouldn't have happened. Like, the design engineer should have damn well measured the output of the ADC clock there. But hey, maybe they did. And it was fine, because a lot of units out there show absolutely no problems whatsoever, and the PLL locks and everything's, you know, everything's hunky-dory. So, but they just didn't test a statistically significant number. So yeah, it slipped through. Oops. It was pretty embarrassing, but yeah, big thumbs up to Rigol for engaging the EEVblog community, ultimately fixing this relatively quickly. So they're a bit premature on the initial beta firmware release, but hey, you know, they did pull it back, which was great, and now they've, well, on my unit. So everyone, please, if you got one of these, try it out. And well, yeah, the review is still out, but you know, this is a pretty darn good scope. As I said, even with those issues, a lot of people still give this scope a big thumbs up. And on mine, I could maybe test it across temperature or something like that. But anyway, keep reading the EEVblog forum down below for updates on this, because that's where all the action's going to happen. So, sorry about the length of this thing. It was supposed to be quick, as all my videos are, but, you know, I get a bit carried away sometimes. Oops. So, there you have it. If you like it, please give it a big thumbs up on YouTube, because that helps. Catch you next time.